class. Class is being recorded now. Of course. So whoever is ready can go ahead.
So question 6.22. The drawing density function of x and y is shown below. For A, are x and y independent? First, I start to solve for the function for x and then for y, which I get x plus 1/2 and y plus half in the range of 0 and 1, and then shows that x and y are not independent. For B, find the density function of x. So since it's solved for x, so we got x plus half in the range of 0 to x to 1. It's a density function of x. Then later we need to find the probability of x plus y less than 1, which is the same as y less than 1 minus x. So I plug into the integrals to solve it. And by doing the integrations, I get 1/3.
Great. Great. Perfect review for last class. Very nice. Thank you. I'm better giving you credits right away because sometimes even I write down, somehow I forgot. So let me give you right away. In this case, I don't forget. Okay, next one.
Can you see my screen?
Yes.
This is question 12. The number of claims received by a car insurance company in amount is a Poisson rundown variable with mean 20. 70% of the policies pertain to vehicle type A, and 30% of policies pertain to vehicle type B. Compute the conditional probability that more than 10 claims received are for vehicle type A, given that at least 5 of claims received are for vehicle type B. And what assumption have you made? So in here we have A and B. If A and B cover all the claims, so we assume A and B are independent event. That's my assumption. Okay, so given at least 5 are B, so 5 is greater or equal to 5, and then more than 10, A is more than 10, so A is greater than 10. Since they are independent, we can just split it and we can solve that. We got this. And to calculate this, we need the mean value in the Poisson rundown variable. So lambda equal to m times p, since in here p is the sample space is just 1, so n equal to 20, and then we calculate the lambda for type A. That will be 20 times 0.7, that's given here, 70%. And we got 14 here, and we just plug into the formula. First of all, we just converted first. So when A is greater than 10 is equal to 1 minus when A is less than or equal to 10. Once we got this, we just plug into the formula. So we got e to the negative lambda, and then times lambda to the I divided by i's factorial, we use a sigma to cover when I is 0 to when I is 10. And then we got this, we subtract this by 1, we got this.
Nice. I have one question.
Yeah.
So on the top expected value, when you calculate, you were saying that equals lambda equals
Yeah.
m times. Oh, that's how you get p equals 1? No, hold on.
That is sample space, because this cover two cases. Case A would be A. That would be this one. Case 2 would be B. So those two cover.
Oh, the probability.
The sum of those two.
Okay. So you get sample space from there.
Yeah.
Got it. Okay. Nice. Nice. Thank you.
Thank you.
Well, Jay, you have reached 20 times. Great. 200%. Next one.
I want to do 6.23.
Okay.
The random variables x and y have joint density function of f of x and y equals 12xy parentheses 1 minus x, where x is from 0 to 1, and y is from 0 to 1, and equal to 0 otherwise. A, are x and y independent? Given that f of x and y equals 12xy parentheses 1 minus x parentheses is equal to the probability density function of x times the probability density function of y. So yes, x and y are independent.
Hold on. How do you know fx, fy?
You mean what they are?
Yeah. Here, fxx, fyy.
Like what they equal to?
Yeah.
It's
Or maybe you mean from here, right? So you have x times 1 minus x. That's for x.
I solved what f of x is on the following. So I solved it for b, in b.
Oh, okay. So maybe you calc b first.
And then for the probability density function of y, I solved it in c.
Oh, okay. I get it. So
yeah.
You have 6x, 1 minus x here. But actually, it's a little bit obvious from the function how is density function defined. Because you can group this x with 1 minus x, then y, just how to distribute this, how to divide this 12. Okay, so you did get from b, you have 6x, so fx. Okay, that makes sense.
Yeah. Okay.
Okay.
So b is find the expected value of x. So since f of x and y equals 12xy parentheses 1 minus x, where y is from 0 to 1, then the probability density function of x will be the integral of 0 to 1 of 12xy parentheses 1 minus x d of y, which we get 6x parentheses 1 minus x. So the expected value of x would be the integral of 0 to 1 of 6x squared parentheses 1 minus x d of x, which equals to 1/2. C, find the expected value of y. So the probability density function of y is the integral of 0 to 1, 12xy parentheses 1 minus x d of x, which we get 2y. So the expected value of y will be the integral of 0 to 1, 2y squared d of y, which gives us 2/3.
Great. Okay, good.
There's also another part, D and E.
Oh, okay.
So D asks us to find the variance of x. So the variance of x equals to the e x squared minus e of x squared. So the expected value of x squared is the integral of 0 to 1, 6x to the third parentheses 1 minus x d of x, which is 3/10. And e of x squared is 1/2 squared, which is 1/4. So the variance of x is 3/10 minus 1/4, which is 1/20th. And then E asked us to find the variance of y. So the variance of y is the expected value of y squared minus e of y squared. So e of y squared is the integral of 0 to 1, 2y to the third d of y, which gives us 1/2. And e of y squared is 2/3 squared, which equals 4/9. So the variance of y is 1/2 minus 4/9, which is 1/18.
Okay, great. Nice.
Thank you.
You're welcome.
Hi, Professor. Good evening.
Hello, Ikara.
I am doing best.
Okay. Then I have a show you. Anyone else like to present today? Okay, let me make a presenters.
Can you see my screen?
Yes.
Can I start?
Yeah, go ahead. Thank you.
I'm going to present question number 25 of chapter 6. Suppose that 10 to the raised to the power 6 people arrive at a service station at times that are independent random variables, each of which is uniformly distributed over 0, 10 raised to the power 6. Let n denote the number that arrive in the first hour. Find an approximation for probability n is equal to I. From the given information, 10 raised to the power 6 people arrive at a service station at the times that are independent random variables, each are uniformly distributed over 0, 10 raised to the power 6. Let n denote the number that arrive in the first hour. The number of people n that come to the station within the first hour has exact binomial distribution with parameters n is equal to 10 raised to the power 6 and the probability of success p is equal to 1 over 10 raised to the power 6. Here the size of population is very large, n is equal to 10 raised to the power 6. The constant probability of success is very small, probability p is equal to 1 over 10 raised to the power 6. So from that we have the formula n multiply p. So when we will put the value, we will get 1. Since n is large and p is small, so use Poisson distribution. So we have to find
Hold on one
probability.
second. So,
Yes,
sorry, Kara. So the sample size is also 10 to the 6?
yes, Professor.
Oh, okay.
So, uh, so we have to find the probability n is equal to I, which is the we have the formula e raised to the power minus lambda, lambda raised to the power I over I factorial. So we have here the parameter of lambda, which is parameter of Poisson distribution, which is equal to lambda is equal to 1. When we put the value, and finally we will get e raised to the power minus 1 over I factorial.
Why still I factorial? Isn't that n equals to 1?
N is equal to 1. This is the parameter of Poisson distribution, and we have to find that in the question. N is equal to I.
Oh, equals to I see, I see.
Yes, yes, Professor.
Oh, okay, yeah, the sample space, yes, it's a 10,
Yes, Professor.
10 to the 6. So consider from 0 to 10 to the 6. I see.
Yes,
All right. Okay, great. Thank you.
thank you.
Can you see my screen?
Oh, I'm giving the credits. I'm just afraid to forget. Yes.
Okay, so can I start?
Yeah, go ahead.
Okay, so I'm going to present 6.18. Let x1 and x2 be the independent Poisson random variables with each xi having parameter lambda I. Find A, the probability of x1, x2 equal to 0. So in this question, we use the Poisson distribution, which is this, and the probability of x1, x2 equal to 0, which is equal to the probability of x1 equal to 0, x2 equal to 0. So
Hold on, really? Because this is x1 times x2 equals 0, right?
maybe
Because
either,
we only need one of them to be 0.
yeah.
But in your case, it's like both of them have to be 0.
Mm-hmm.
Yeah, this is just one case, right? Both of them can be 0, or one of them to be 0. So you should have 3 cases.
Okay.
Okay, but keep going. You
So,
can fix it later.
so in here is the case 1 when both them are equal to 0. So I just plug in the lambda 1 into and 0 into the Poisson distribution, and lambda 2 and 0 into the Poisson distribution. So in this case, we will get which is equal to the e to the power of negative lambda 1 plus lambda 2. And I think when x1 equal to 0, just keep this, and x2 like
Can be anything.
put some number like k or a, put some number
Yes,
into this, then
that's
make
right.
up, yeah. And
Yeah.
x2 is equal to 0 is similar.
Exactly. Nice. We fixed it right away.
And B, the probability of x1 plus x2 equal to 1, which I use the formula in the textbook, which is the probability of x plus y equal to n is equal to this. So in here, I just plug in when n equal to 1. So the probability of x1 plus x2 equal to 1 is equal to the e to the power of negative lambda 1 plus lambda 2 times parenthesis lambda 1 plus lambda 2 to the power of 1, and over the 1 factorial. So we will get the answer is e to the power of negative lambda 1 plus lambda 2 times the parenthesis of lambda 1 plus lambda 2. And C, the probability of x1 plus x2 greater than 1. So the probability of x1 plus x2 greater than 1 is equal to 1 minus the probability of x1 plus x2 less than equal to 1. So the probability of x1 plus x2 less than and equal to 1, which is equal to 1 and equal to 0. So the probability of x1 plus x2 equal to 1, which we find in question B. And when x1 plus x2 equal to 0, I just use n equal to 0 into the formula in the textbook, then make a calculation. We will get the final answer is 1 minus e to the power of negative lambda 1 plus lambda 2 times parenthesis 1 plus lambda 1 plus lambda 2.
Great.
Mhm.
Very nice. Very nice. Thank you, Xiuyu.
Thank you.
Hello, Professor.
Hello, Catherine.
Okay, so I'm presenting 6.9.
Okay. Are you graduating, Catherine?
By the end of this year, I'm graduating.
Oh, okay. Are you? Yeah.
Okay. So 6.9, the joint probability density function of x and y is given by fxy equals to c times x times e to the negative y power, and 0 is less than y, less than or equal to y, less than or equal to x, and less than or equal to 1. So for part A, we have to find the c. So we set up the integral and we put our c in the outside the integral. C times the integral of lower limit bound 0 and upper 1, and then 0 to x, x times e to the negative y, dy dx equals to 1. And solving this integral give us that the c is equals to 2e over 4 minus e. And then for part B, we find the marginal density of x. We know that fx equal to c times the integral of 0 to x, x times e to negative y dy. And then we already know our c, and then once we solve this integral, we get that for the marginal density of x, we have 2 times e times x times parentheses to 1 minus e to the negative x over 4 minus e. And part C, we do the same thing, but with the marginal density of y. And for C, if fy equal to integral of lower limit bound y and the upper limit bound 1, c times x times e to the negative y dx. And since we already know our c is 2e over 4 minus e, solving this integral give us that the marginal density of y is parentheses 1 minus y squared times e to the negative y over e to the negative 1, and then times 4 minus e.
Since you have this as a fraction, my suggestion for you for next time, you would move e to the negative y to the denominator to be e to the y, then move e to the negative 1 up in the numerator to be e,
Yeah.
right?
Yeah.
Okay.
Okay. And then for part D, this is a conditional probability. That's from 6.4 section, but I did it anyway. And for this one, we have probability that y is less than 1/3 and x is less than 1/2. And for this one, we use conditional probability. That probability y is less than 1/3 and x is less than 1/2 over probability x is less than 1/2. And then we set up our double integral. Integral of 0 to 1/3 and 0 to 1/2 c times x times e to a negative y dx dy over the integral of 0 to 1/2 c times x times parentheses 1 minus e to a negative x dx. And solving this big integral, we get that the result is 1.02. And then for part E, we find the expected value of x. We know that, so we have integral of x. We know that expected value of x is equal to integral of x times fx dx. So we know from part B and part C, because we need to find expected x and y. For this one, for E, we know that fx is c times x parentheses 1 minus e to a negative x, and then we plug this into our expected value integral. We get that result, and we plug in the c. We get the answer is 0.7327.
Okay,
And
this is
finally,
pretty good. All right, you finish.
huh? Oh, we have
Yeah,
part
I
the
thought you
last one.
finished. Yeah, you have
Okay,
F.
so
Yeah,
for
finish
f, we get that for the expected value for y, and then we set up the integral like so integral of 0 to 1 y times f of y dy. And since we already know our c in here, and we know that fy is c times e to the negative y parentheses 1 minus y squared over 2. We plug this in and solve this integral. It gives us results 0.3188.
Good job. Okay, let me ask, anyone has any questions? So I think you are supposed to. I have one question, Catherine.
Yeah.
You see the first line on this? If you go up a little bit, there's one more line. Yes. Okay, D.
Yeah. For
So
D?
is this condition or this is the end? Because you read
And?
end.
Oh,
This is
yeah, because
condition.
it's like intersection. This is like, you know.
This should be conditional, right?
But yeah, conditional.
So the second one is end, right? They are
Yeah.
equal to the second one. It should be end. The first one, the vertical bar should be condition, and the second one is end. This one you should read the end on top of this second line. Yes, right?
Oh, I should do that too.
Makes
Oh,
sense?
okay.
Yeah, this is not a conditional. The conditional one is the first one. You should switch this end and the conditional probability. Okay, anyway, very nice
Oh,
question. Anyone has
okay.
any question about this? This looks like exam question. Okay, Catherine, let me give you credits. 150. All right, next one. Who's going next? We have Tom, we have Ice. That's it, only you two. Anybody else like to present? Andreli, or Darius, Ayat, Chanel, Emma, Raul, Impin, Zakia? Okay, this is Tom. I can tell by the paper.
Yeah, it's me.
Yeah.
Okay, so the problem is the random vector xy is said to be uniformly distributed over a region R in the plane if for some constant c, its joint density is c if x, y is element of region R, 0 otherwise. So part A, we have to show that 1 over c is equal to area of region R. So for part A, we have double integral over region R of the fx, y dx dy is equal to 1. So the distribution is fxy is equal to c is given. So we can factor the c out, and then we have the double integral of r. Let me draw this. So factor c out, and then this region over r. I can't really write it easily, but that would be equal to a, the area. So we have 1 is equal to c times a. Then we rearrange to get 1 over c is equal to a. That's part A. And then part B, the question is, show that x and y are independent, with each being distributed uniformly over -1, 1. Okay, so we want to show they're independent over -1, 1. So we want to show that the joint distribution here is equal to the distribution x times distribution y. So we have a square centered at 0, 0 with sides of length 2. That's given. So we have area is equal to 4. So from part A, we have A is equal to 1 over C. So C is equal to 1 over 4. And so we basically have fxy is equal to 1/4 because we're given that fxy is equal to C. So we solved that part to get 1/4. Now we just need to figure out fx and fy and see if it's equal to 1/4. And so we plug in the integral over the region 1 minus 1, and this part times c dy. That's to find distribution function for x to get 1/2. We repeat this process for the y. It's symmetrical, so it's also going to be 1/2. So then we have, so now we're just checking if this identity is true, which was 1/2 times 1/2 equals 1/4. And it is equal to c, which is 1/4. That's given. So we confirm that that x and y are independent because fxy is equal to this identity right here, fx. And part C, we are finding probability that it is also in a circle of radius 1, centered at the origin. That is, find probability x squared plus y squared is less than or equal to 1. So in words, we're finding that the point is in the circle and in the square in part B. And if they're independent, we multiply the joint distribution by the probability that it's in the circle. So from part B, we had 1/4. So now we just need to find this probability.
Why 1/4 is not your integrand?
1/4 was from part B, joint distribution for x, y.
Right, because you have no integrand which is 1. So this means you are trying to find area of this x squared plus y squared less than or equal to 1. Oh, okay, indeed. You want to express that equals to 1. Sure.
Yeah.
Okay, go ahead.
Yeah, we're gonna find the area of
right.
circle. Yeah. So the area of the circle region is pi r squared, where r is equal to 1, because we're given that the radius is 1, I think. Yeah, so less than or equal to 1. That's why the radius is 1. And then so the area is equal to pi. So then we multiply pi times 1/4. 1/4 was the probability it was in the square from part B, and then we get pi over 4.
Hold on 1 second. I don't think I'm agreeing with you. What I would do is I wouldn't do this equals 1. I would do probability of x squared plus y squared less than or equal to 1 is the double integral over x squared plus y squared less than or equal to 1. I would put 1/4 as what? As the integrand.
I'm confused. So this is the area of the circle, right? So
right. So
this
right.
Is equal to pi. Or I think I think you have to put c in here. That's why.
Right, you have to put a quarter there, right? Because C is based on B, right? C is based on B. You already find your density function is quarter. Shouldn't you put a quarter inside as integrand?
We're multiplying.
Which it doesn't change anything. Yours is exactly right. You just multiply quarter in the end. You know what? Don't bother. Because quarter is just a scalar. You can put outside the integration. Yours is exactly right. I agree with you now. Yeah.
I think this is supposed to be equal to A. I'm not sure, right? But
okay, you did it in two steps, but in my head, I was doing in 1 step. Anyway, yes, yours is exactly right. We just do differently. We just have different thinkings. Yes, I agree with you. It is pi over 4. Yes, Tom, thank you. Thank you, Tom. 160. Okay, anyone else? Ice, right? Okay.
Yeah, I can go.
Okay.
Yeah, I can go.
Okay. Anybody else? Andrili, Darius, Ayat, Chanel, Emma, Raul, Yinping, like here, because you don't have many. We only have 6 more classes, I think.
Okay, so I am presenting question 6.13. And it says a man and a woman agree to meet at a certain location at 12:30 p.m. If the man arrives at a time uniformly distributed between 12:15 and 12:45, and if the woman independently arrives at a time uniformly distributed between 12 and 1, find the probability that the first.
Oh, we lost you. I spilled my water.
No.
Oh, you're back. Oh, we lost you again. Probably have an internet problem.
So for this question, I set the
I see your voice is on and off.
Is this better?
Yeah, keep going. I can hear you now.
Okay, so for this question, I set the man as S and I set the woman as T. And as the question gave, the variable for S is from 15 to 45, and the variable for T is from 0 to 60. And the first part of the question is asking to find the probability that the absolute value of the difference between S and T is less than or equal to 5. So in order to do that, we would need to find the joint probability distribution. But to find the joint probability distribution, we would first need to do the probability distribution of S and T separately. So that over here is just 1/30 for S and then 1/60 for T. And then the joint probability distribution is 1/1800. And to find the desired probability in the question, I expanded on the bounds of it for T. And I set it up as 45 to 15 and then T plus 5 and T minus 5 for the bounds. And I took the integral of T and I took 1/1800 out as a constant, and it simplified to 1. And further simplifying it, you get to 300/1800, which simplifies to 1/6. And then for part B, it asks, what is it? Where you're calculating the probability of S is less than T. And the bounds for that would be from 45 and 15 to 60 in S. And that would follow the same steps, and it simplifies to 1/2.
Okay. Okay. All right. Thank you, Ice. Anybody else like to present? Okay, if not, it's my turn. So we're going to talk about the sums, I think. Some of you already are doing ahead of us. Okay, I think we're here, right? If I'm not making mistakes. Sums of independent random variable, which some of you already ahead of us. Okay, let's read. It's often important to be able to calculate the distribution of x plus y. This looks so familiar. No, we didn't do this. Okay. From the distribution of x and y, when x and y are independent. So suppose that x and y are independent continuous random variables having probability density functions we use f from x, f from y to represent each distribution function. The cumulative distribution function of this, which some of you already used, so it's obtained by this: x plus y less than or equal to a is the double distribution over this region, and the density function of f for x and for y, the product of those two. Oh, okay, we didn't really use this yet. All right. So this suppose both of them run over the real x-axis, right? So y goes from -infinity to infinity, and the x goes from this is important, right? Because this one we can write as y or x less than or equal to, or x less than or equal to a minus y. All right, that's why we have this. Okay, so if we rewrite this, we can write it as x less than or equal to a minus y. So that's why this for x-axis is going from -infinity up to a minus y, because it's less than or equal to. Okay, so because this is density function for x, this is density function for y, so we can write this way. Okay, right? We can just integrate this part, then this part. So then in the end, what do we get? We get anti-differentiation of little f, which is a capital F, use cumulative, right? F, capital letter F to represent x, takes a minus y as variable, as the input, right? Then of the y distribution. Well, you could argue, right? It's the same for y. We could write it in another way. We could write this one as fy of a minus x, fx of x, then dx. Right? Because, you know, x and y are equally weighted and they're independent. So the cumulative distribution function of f, capital letter F, x plus y is called a convolution. Right? So that's on our syllabus. It's called a convolution. So a fancy name of the distributions of fx and fy. So the cumulative distribution function of x and y. So by differentiating this one, 3.1, we found the probability density function of x, little f of x plus y of x plus y is this, right? This. Remember, where does this a come from? All right. This a comes from this, from this part, from the convolution. So this represents the density function. Fx, a minus y, fy, y, dy. All right. You may argue you could write this fy of a minus x, fx of x, dx. Let's see this one. Identical distributed uniform random variables. So it's not difficult to determine the density function of the sum of two independent uniform 0 to 1 random variables. Let's see this one. So that's the sum of two independent uniform random variables, x and y, from 0 to 1. So we want to calculate the probability density function for x plus y. So fx, fy, both of them are uniformly distributed. Then we have this. We can calculate. Okay, we can calculate. So from 0 to 1, the integration of x, a minus y, dy. And so for a, it's in from 0 to 1. And we can rewrite this as 0 to a dy. So this is same. Okay, because a is going from 0 to 1. Okay. Okay, why this is true? Y goes from 0 to 1, A goes from 0 to 1. Oh, of course. This equals to, because the density function of f of x, f of y is uniformly distributed, is just 1, uniformly distributed. All right, we get this, right? Because this is because this density function is uniform, is 1 over 1. All right, so get this, then, so that means, so this the density function for this convolution is just A, identity, right? Identity. So it makes sense because both of these density functions is just 1. Okay, let's see. For A from 1 to 2, let's see what do we get. From A from 1 to 2, so f of x plus y a, the lower limit is a minus 1, because a goes from 1 to 2, and the upper limit goes to 1. Then that just equals to 2 minus 8. All right. So hence we have this. We have f of x plus y, because x goes from 0 to 1 and y goes from 0 to 1. All right, so x plus y can go from 0 to 2. So if a goes from 0 to 1, we just get identity function. If a goes from 1 to 2, we get this linear function, 2 minus 8. So in this case, the random variable x plus y is said to have a triangular distribution. And suppose that x1 up to xn are independent uniform random variables. So this, the finite sums, the finite n sums, or the n convolutions, so we get this. Fn of x equals to x raised by n divided by n factorial. For the x value goes from 0 to 1. F of n minus 1 would be x to the power n minus 1 divided by n minus 1 factorial. So triangular density function. Now we can write like this. Summation of this n of xi's. Of course, we can write from 1 to n minus 1, right? Because this is n minus 1 of them. This is the last one. So we can write this way, fn of x for n minus 1 of them, then times the last one. So this is a little proof of this. Little proof for this. Okay. For this is a finite many independent uniform random variables. All right. An interesting application of this, so let's use to determine the expected number of independent uniform from 0 to 1 random variables that need to be summed to exceed 1. So with x1, x2 being independent uniform random variables, we want to determine expected value of n of them. N equals to minimum of such n, which for this, the least finite number of x adds up greater than 1. So n is greater than, little n is greater than 0 if and only if this adds up all those less than or equal to 1. So we have this probability of n greater than n equals to this, which is 1 over n factorial. Why? Because for this n, how many number of finite variables, right, is greater than 0, at least 1. So equals to 1. Then probability of n equals to n is probability of n greater than n minus 1 minus greater than n, which we use this one, which we use this one, so we get 1 over, we use this one, which we use this one, we get 1 over n minus 1 factorial minus 1 over n factorial, which is n minus 1 over n factorial. So the expected value we have n times n minus 1 divided by n factorial, adds up all those. Then we can simplify this. So n divided by n factorial, n minus 1, so that's 1 over n minus 2 factorial by simplification. This is because we have a minus 2 now, we have to re-index. Well, infinity just goes to infinity, so we don't have to adjust the infinity sign, but we have to adjust the lower index, because we don't allow, in the summation sign, we do not allow negative number. Index goes to a negative number. And this one somehow, if we remember series, that equals to E, all the number. So this means the number of independent uniform random variable must summed for the sum to exceed 1 is equal to E. Interesting, huh? That's for uniform distribute. Let's see, these gamma random variables. Remember, gamma has this fancy distribution. And y, so what's important to remember is y is a positive number. The important property of this family distribution is that for fixed value of lambda is closed under convolutions. Let's see, what does this mean? It's closed under convolutions. If x and y are independent gamma random variables with respected parameters s lambda, t lambda, then x plus y is a gamma random variable with a parameter. Oh, okay, that's nice, right? X plus y, just adding x and t. Use equation 3.2. I just want to go back to see 3.2. This one. X plus y of a equals to this. Oops, what did I do? So we use that, and right, we see this one. We see this is a minus y, x minus 1. Then that's the later part of t minus 1. Then we simplify this. This is from the gamma distribution. Right? We have gamma 1 over gamma s, 1 over gamma t. Okay, this is just rewrite stuff. Anyway, this is a complicated, so but This is just f of x plus y for gamma distribution. Okay, so the convolution for gamma distribution. So what is the c? C is a constant, does not depend on this such a. So we get this, right? Get this formula. Get this formula. See what's changed is, so a is here, a is here. We see this is x plus t minus 1, and the gamma of x plus t. That's very nice. So it's saying it's now a simple method to establish by using proposition 3.1 and induction. Let xi, so I goes from 1 to n, independent gamma random variables with respective parameters ti and lambda. So that's a finite many. Okay. So that means, you know, can go with finite. You know, of course, if we can go with 2 of them, that means indicates we can always use induction. That's intuition tells us we can go with the finite many unless some conditions required. Let's see this example. So we have n random variables. It's exponential now. So we talk about uniform, Poisson, now exponential random variables. Each having parameter lambda. Then since an exponential random variable with parameter lambda is the same as a gamma random variable with parameter 1, because it's a special case of gamma distribution. 1 lambda, it follows from proposition. So the sum of n variables is a gamma random variable with parameters of n lambda. Okay, because we have n variables, so that becomes n lambda. If z1 up to zn are independent standard normal random variables, then y equals to this zi squared. So this is squared. It's said to have the chi squared. Okay, this is the famous stuff. Chi squared distribution, right, with n degree of freedom. So now let's compute. Right, n equals 1, y equals z1 squared. So then fz square of y equals 1 over 2 square root of y, fz square root of y plus fz negative square root of y, because we have a z squared. So that adds up to something like this. And we recognize the preceding as a gamma distribution with parameter half. Oh, okay, so you see this is negative y times half, right? Half minus 1. And this is also half, y times half. This is also half. So that's just gamma distribution with half. A byproduct of this is gamma of half equals square root pi. Okay, this is something else. This is with number 3. You use this a lot. Gamma half equals square root pi. There's some other calculations which is very fun to do this. But since zi squared is a gamma distribution half, it follows from 3.1. The chi squared distribution with n degrees of freedom is just the gamma distribution with parameters n divided by 2 and a half. Isn't this interesting? Exponential distribution, gamma distribution, chi squared distribution, they are cousins. And hence has a probability density function with this involve gamma of n over 2. Right, so the parameter of gamma is n over 2. Then we still see this n minus n over 2, n over 2. When n is an even integer, gamma of n divided by 2 is n divided by 2 minus 1 factorial. Yeah, if any of you interested in going to number 3, a direction in mathematics, those are important for you. And also there are proofs of this, very nice. Whereas when n is odd, gamma of n divided by 2 can be obtained from iterating the relationship of gamma of t equals to t minus 1 times the gamma of t minus 1. And then using the previous obtained result, gamma of half equals square root pi, Example, gamma of 5/2 equals to 3/2, gamma 3/2, so on and so forth. In practice, the chi-square distribution often arises as a distribution of the square of the error involved with one attempt to hit a target in n-dimensional space, when the coordinated errors are taken to be independent standard normal random variables. It's also important in statistic analysis. Anyway, chi-squared. We only need to know a little bit. Okay, next come normal random variables. Okay, normal random variables is the king in the end. We can also use equation 3.2 to prove the following important result. Xi, n variables are independent, normally distributed, and we have these mu i's, sigma I squared, and then the sum of xn of random variables is normally distributed with parameters of this sum of mu I and the sum of the variance squared, sigma I squared. Nice, isn't it? Yeah. The proof of this. Okay, I'm not gonna go over it. If you're interested, you can go over it. All right. This is a, if you're interested, you can go over this. But this result is important for us because again, normal random variables, normal distribution is the king of the probability world. And the convolution of n variables, yeah, just this, just linear, just adds up the mu I, the mean, adds up the variance. All right. Let's see this example. A basketball team will play a 44-game season. 26 of these games are against the Class A teams and 18 are against the Class B teams. Suppose that the team will win each game against a Class A team with a probability of 0.4 and will win each game against a Class B team with probability 0.7. Suppose also that the results of the different games are independent. Hold on. Suppose that the results of the different games are independent. Okay, so this is has nothing to do with the probability because this is 0.4, this is 0.7. Approximate the probability that A, the team wins 25 games or more. B, the team wins more games against A, Class A team, than it does against Class B team. So we use variable XA, XB denote the number of games teams wins against Class A and against Class B teams. Then XA, XB are independent binomial random variables. So expected value of A, XA is 26 times 0.4, right? Because it wins at least 25 games or more. So 26 times 0.4, get this. Variance, 26 times 0.4 times 0.6, P and 1 minus P. Right? Remember how do we calculate that? 6.24. Expected value of XB, 18. Because how many games? 44 games. Right? 44 minus 26, that's 18. 18 times 0.7, so get this. 18 times 0.7 times 1 minus 0.7, we'll get this. So by the normal approximation to binomial XA, XB, we'll have approximately the same distribution as we would independent normal random variables with the preceding expected values and the variance. So by proposition 3.2, the sum of those two will have approximately a normal distribution with mean 23, variance 10.02, right? If we use the to calculate. Therefore, if Z denote a standard normal random variable, so we would have but this z-score changing to z-score. So that's it's the same as a z-score greater than 1.2 divided by this. The same as 1 minus z-score less than this. So go to the standard normal table. And that's this. Okay, so probably you have homework like this, or you could choose homework like this to do, all right? Log normal. So the random variable y is said to be a log normal random variable with parameter mu and sigma if log of y is a normal random variable with mean mu and variance sigma square. That is, y is a log normal if it can be expressed as y equals e to x. Okay, I don't think this is important to us because the syllabus didn't mention this. And in this case, x is a normal random variable. Okay, let's see this example. Starting at some fixed time, let x of n denote the price of certain security at the end of n additional weeks. So n is greater than or equal to 1 week. A popular model for the evolution of these prices assumes that the price ratios x of n divided by x of n minus 1. So n is greater than or equal to 1 are independent and identically distributed log normal. Okay, forget about this. (6.34) Okay, Poisson and binomial random variable. So this thing, rather than attempt to derive a general expression for the convolution of x plus y, in the discrete case, we shall consider some examples. Let's see. Sums of independent Poisson random variables. If x and y are independent Poisson random variables with respective parameters number 1 and number 2, compute the distribution of x plus y. Because the event x plus y equals n may be written as a union of the disjoint events. So x equals k, y equals n minus k, k goes from 0 to n. So we would have probability of x plus y equals n. It's the sum of this index goes from 0 up to n. Yeah, because k goes from 0 up to n. Probability of x equals k, y equals n minus k. And that is, because they are independent, so that is this. And then with the Poisson distribution, P of x equals k is this. And equals n minus k is this. Now we can do some calculation. So in the end, wow, in the end, that's, I think Xiu Yu used it, right? Xiu Yu used this. Yes, okay, great. Oops. Yeah, so that's for Poisson convolution, all right? So we have this nice formula. Number 1 plus number 2 divided by n factorial. Well, I would write this way. Well, that's okay, actually. I would write the number 1 plus number 2 raised by n divided by n factorial divided by e to the number 1 plus number 2. But anyway, so this is nice, stuff like that tells you mathematics should be simple. The real mathematics, the true mathematics should be simple. Anyway, this is beautiful. Okay, let's see. Sums of independent binomial random variables, x, y binomial independent. We want to calculate the convolution. Let's see. And because it's independent, okay, this is defined as this, because it's independent, so we have this. Then binomial for x equal to I, binomial for equal to k minus I. Then maybe you can do something. This is saying, okay, let q p1 minus p. Then we can rewrite that, or we can write this one. Then we can rewrite this. And the conclusion follows. Oh, okay, then that's this. So that's this. Let's see. That's p to the k, q to the n plus m minus k. So what's q? Q is 1 minus p. N plus m minus k. And the index goes from 0 up to n. And then out of n, choose I. Out of m, choose k minus I. Okay. Nice, huh? Okay, so then what is this? Out of n, choose I. Out of m, choose k minus I. For the summation of all this, I equals 0 to n. That is n plus m, choose k. Yeah, I remember this tells a story about the song. I don't know if anyone knows the song, Christmas song. Tells you have how many days? 12 days. You get all different gifts. Yeah. So this equation has a story. That story, Christmas gifts, song story. Anyway. Okay, so this is nice to know, right? So this one, you could just change this one to be this. Out of n plus m, choose k. It would be so nice, right? So p to the k, q to the n plus, well, q is 1 minus p. Maybe we just use, p to the k, 1 minus p to the power n plus m minus k. Then out of n plus m, choose k. You see how nice? So this is for sums of a binomial. Okay, sums of binomial, of course, independent binomial random variables. So Poisson, sum of independent Poisson, very nice. Sum of binomial, very nice. Normal, very nice. You see this simplified. Okay, and that's it. That's all for today. Anyone has any questions? Okay, I see Andrea left. Okay, anyway. Okay, so please, if you haven't get 100% for your presentation, I think you should. I think that's an easy. I mean, it's not easy because you have to do your homework. You have to pick one to present, right? And please keep doing it. All right. Okay, if you have no questions, you are free bird for tonight. If you do have questions, I'm here.
Professor?
Thank you. Yes.
So